Very good. Thank you. Fantastic. So that's the equation most of us think of, I think. Those of you who've seen this before in your calculus or physics classes in the past. This equation is, I think, the canonical constant acceleration expression, but there are others, and it's useful to have a variety of them. The reason is that you'll be faced with problems where you aren't necessarily told what x naught is and v naught is and t is and a. You may not know all those things. You only know some subset of them. And so what you want to do is combine different equations or have at your disposal a variety of different equations so you can actually get your answer. All right, so let's make our list of constant acceleration equations. The book has the same pantheon in chapter 2, I think it is. So yes, once again, what's wrong with that? X equals, okay, this is the same equation we did 10, v naught t plus 1 half at squared. And then we've got, we have another equation that's very useful, I told you, which is just v equals v naught plus at. But what else do we have? Well, we also know the definition for average velocity, right? Average velocity is, let's see, is that the one I want? I think that's the one I want. Average velocity is delta x over delta t. And given our current notation, so right now we're using a notation where the initial time is equal to 0, so it's not appearing in our equations, and our final time is equal to t. So I can rewrite this as just t on the bottom, and then for this I just say x minus x naught, right? And this expression, by the way, this is always true. This is a definition even, right? Always true. One L? Two L's? You're not going to lose points for spelling. Unless the grader can't tell what you wrote. That's the only way. But they can tell what this means, whether it's 2 L's or not. So great. That's always true. But for constant acceleration, there's another way we can write down the average velocity. Because look, for constant acceleration, velocity is changing linearly, right? That means that if I want to know what the average is between time 0 and some later time, well, you can just do a symmetry argument, right? You can say, well, I know what it is here and here, and I take the average of these two values, I get values right in the middle. What about this value and this value, this value and this value? In all these cases, if I take pairs that are equal distance away from the center of the line, they each individually average out to this middle value. Does that make sense? So when you take an average, that's one way it's a quick way to get what the average is if you have a bunch of numbers that are evenly distributed. In other words, if you make a plot of them and it makes a straight line on a graph like this, another way to write the average velocity is the initial or the final velocity plus, this is not a minus sign, plus the initial velocity and divide by 2, right? So if I want to know what's the average velocity between this moment and this moment, right, up here, and maybe this is time t right here, and here's my t naught right here, otherwise known as 0. Say, what is that? Well, it's whatever the average is of these two values. So that's just this value plus this value divided by 2. And that gives me my average, right? The book goes through this, but I think it's worth pointing out in class. You can see it. So I don't like to go through all the derivations of everything. I'm not going to spend the whole class doing derivations and mathematical stuff. But anyway, I'll do for things I think are useful enough. I'll do them in class. So this right here is a nice way for us to then combine. We combine this with this expression. Oh, and I should be clear. This is only true. This is only for constant acceleration. So we're allowed to use it here because we're trying to use it in conjunction with other equations that are also only true for constant acceleration. In fact, why don't I label that so it's clear? These are only true for constant acceleration. Right? And that's important. You'll come up with problems in this class where you have to think about, wow, is this constant acceleration or not? Right? Am I allowed to use these equations? Because you can get some crazy answers if that's not valid, right? But given that this is constant acceleration, we can use this. We can always use this if we relate these two things and just set them equal. So if we just combine these two equations, right? Then we wind up with an expression, it gives us another relationship between these various variables, and I'll just write down the result. The result is that x equals x naught plus 1 half, right? That 2 turns into this half, times v naught plus v. Okay? So that's another expression. Why is that useful? Well, suppose you're given a problem, right, where you're asked to find some distance, right? And you know what the initial velocity is and the final velocity, and you know the initial position, but you don't know the time, right? Well, these equations up here require you to know the time if you're going to try to calculate x. Actually, this doesn't even have x in it, so trying to find a distance, this one will help you anyway, right? So it depends on what you're looking for and what you're given in the problem description, which problem you're going to use. Now, we're doing problems today that are simple enough that you can just sort of grab the right equation out of the text and that solves our whole problem. We're going to do problems like that. We've already done a couple problems like that. Those are so simple I just wrote down answers I haven't calculated, right? But at some point, we'll have, like in the homework next week, Friday's homework next week, there are some problems that you can't just take one equation. You can't find a magical equation somewhere in the text that's going to solve the whole problem. You'll have to do it in stages. And you'll have to have a plan of attack. There's a problem with the flower pot. That's my favorite on there. That problem requires you to go through stages and think through, get a strategy for how to build up partial information to finally get the answer you want. But anyway, the way you always start, though, is by seeing what the equations depend on, and you have your little list of what do I know and what am I trying to find. Okay, great. So there's a fourth equation I'm going to write down, and that is if I combine this one with, if I combine 2 and 3, these two equations right here, then I can use some algebra, and out comes another expression. And that's v squared equals v naught squared plus 2 times acceleration x minus x naught. Yeah. Am I? I probably am. Because, yeah, of course I am. Because that's meters, and that's meters per second. There better be time on top. Let's see if I got that right. Yeah, absolutely. That was a long time for me to have a bogus equation up there. Go ahead and speak up. But thank you very much. Yes, you're absolutely right. So that's right. If I have meters here, and I've got meters per second, you know there's going to be something to offset that. There's got to be seconds in there. There's only one item with seconds in it in this whole problem. It's just t, because we said t not equal to 0. So that's the only thing that could have been. Good. All right. So these are the canonical equations we're going to use for constant acceleration. Let's see, we've drawn our pictures of those things. And so what situations give us constant acceleration? We've already talked about one. If I throw this chalk in the air, right? Or anything in the air, right? So Galileo, somewhere around 1600, a long time ago, figured out, just empirically, by dropping a whole bunch of stuff, that it doesn't matter how big something is or what shape it is, provided there's not, well, he didn't phrase it in terms of wind resistance, but we now will think about it. As long as if you drop a feather, it doesn't fall very fast, right? So that might fool you, and it fooled Aristotle into thinking that the gravity acts differently on different, well, I should be careful I say that. It does act differently, but that the resulting acceleration is different. Aristotle didn't have acceleration either, but that's fine. So it turns out acceleration from gravity is the same for all objects if that's the only force that's acting on the object. So if you drop something off the tower, it doesn't matter if it's really massive or if it's really light, provided that you can neglect forces from the wind. You can neglect wind resistance. The acceleration is defined up there, right? Of dv dt. This is the motion of the object. Forget forces. The acceleration of the object is going to be 10 meters per second squared, straight down. Now, whether you call it positive or negative acceleration depends on your choice of axes. If I decide to define let's say I define my x-axis to point up, and I want to talk about the acceleration of this piece of chalk as it's falling, then I would say it has a negative acceleration. Why? Because the second derivative with respect to time of its position x is, x is getting smaller, right? It's a negative acceleration. I shouldn't say x is getting smaller. The velocity is getting smaller, right? So it starts off, let's think about this. I drew this picture right here for constant acceleration in a situation when you start off with a negative velocity, and then you go through a 0, at one moment in time you go through 0, and then it gets positive again. But there's other shapes I could have gotten if I had different initial conditions. If I started off going in the positive direction, suppose I had a positive velocity to start, then it never would have gone through 0, it just would have gotten faster and faster and faster. It's just like you step on the accelerator in your car, you accelerate a constant amount. If you start at 0, well, suppose you started off already moving, you're coasting along, and you accelerate. You're going to go through 0, you just go faster and faster and faster. So the shape of that curve has a lot to do with the fact that it's constant acceleration. It's a parabola, as a result. But the details of where the 0 point is, or if there's no any 0 point at all, or I shouldn't say 0, I should say a minimum. Right? The fact that it went through a minimum, that only happened because of the initial conditions. So positive acceleration happens to be going, if in this case, if you're accelerating upward, gravity is always pointing down. If you choose to have upward be your positive x direction, then you always, in this problem, you're going to have negative acceleration. So let me ask you this then, given that. Students, this is a confusing point for many students. If I start the chalk going upward, it has then a positive velocity, right? And so tell me, is the acceleration positive or negative right as the chalk leaves my hand? I agree. What about after it's on its way back down? Yeah, right on. That's exactly right. That's good. Did you learn that today or did you learn that from childhood? You did the reading. It's a beautiful thing. But students often will, when I come to office hours, they'll ask me, they'll go to the board, I can't solve this problem. I keep getting the wrong answer. And the problem is that they change the sign of their accelerations based on which way the chalk is moving, right? The thing is, when we drive our car, all of us drive cars pretty much, there's an accelerator, and there's a notion, and there's a decelerator to brake. People think about deceleration. So in this class, we won't talk about deceleration. But when you're in a car, you often imagine, the x-axis sort of implicitly is always pointing forward, out of the headlights, it's forward. And so that means that whenever you hit the gas and your car speeds up, people tend to think of that as, okay, acceleration means you're speeding up. And when you hit the brakes, they say, I'm slowing down, I'm decelerating, because of negative acceleration. The problem with that is that as long as the x-axis that you define your problem happens to be in the direction that you're moving, that logic makes sense. But when you have an object that's moving in the opposite direction of your positively defined x-axis, which often happens 50% of the time, so it happens in physics class, right? Then it all reverses. And the acceleration, so in other words, when this guy's going up, his acceleration, given that convention right there, is positive, is negative, and the acceleration remains negative on the way back down. What about right at the top? Right at the top when the chalk has 0 velocity, right now, right? What was the acceleration at that moment in time? So I'm hearing both answers. The answer is negative 10 meters per second squared. This is constant acceleration. There's no little blip. It isn't like we go along here and say, went to 0 briefly and went back up. No, it stayed at 0. It stayed at some non-zero value. The way to think about it is that if you look at the motion of the chalk right before it reached its maximum, right, it was moving upward. If you look right after it reached its maximum, it's moving downward. Just like Jenny was moving in one direction initially and then a different direction later, right? Even if you make that interval of time shorter and shorter and shorter on both sides of that moment when it was holding still, it's still the case that you've got this curve that's bending over. And it's that bending curve, right, in the x versus t, right, curve I'm talking about, that bend tells you there's some acceleration, even if it's not moving at the very moments that you're talking about. The fact that it's that curvature, that tells you the acceleration is non-zero. It also tells you what the sign is. In this case, see how the curve is curved upwards? It's like a cup, right? Concave up, right? So that tells us that the acceleration in this problem, in this description here, is positive. I was consistent about that, right? Positive slope for velocity, upward curvature, right, for the x versus t. Good, self-consistent. Now, if I use this convention, and I'm talking about this piece of chalk I'm throwing in the air, right, and I make plots like this, then it's going to be all upside down from this, right? Because with this convention, the acceleration is in the negative x direction. I would have had a negative value for a here. I would have had a downward sloping straight line here. And I would have had a downward curved curve up there for the x versus t, right? So keep track of that stuff when you're thinking through these problems and everything. You've probably all seen it before, but it's good to be reminded. It trips a lot of people up to keep their signs straight. And students really, they'll even change their answers. They're halfway through the problem, they'll just change the signs on stuff. Because it's so uncomfortable for them to think about negative acceleration. But the thing is, the way it works, the way we will describe motion in this class and throughout the entire course, is that we're going to define our axes inside the laboratory frame, or inside like on the Earth, or in some nailed down to some inertial reference frame. And I'll talk more, what does inertial reference frame mean? We'll talk about that when we talk about forces a little bit. But the point is, we're not going to define axes like attached to my body. I'm not going to have an axis on my body, x-axis, where depending on which way I'm pointing or which way I'm moving, the axis changes. Which is the way you think about it when we're driving a car. So that's why, I think that's where the mismatch is between a lot of people's intuition, is that they're used to driving a car and thinking about it relative to the car, right? Okay, and also, we'll use ramps sometimes. So in the case of throwing no. When I'm throwing chalk up in the air, that's projectile motion. And in particular, this is all one-dimensional. So everything so far, when I throw the chalk in the air, I throw it straight up and down. There's only one dimension, just this x dimension. If I throw it at an angle, now I got to worry about x and some other dimension. Maybe I'll call it y, right? So it's all one-dimensional. We'll often have problems, though, where the direction that something's moving isn't necessarily vertical or horizontal. So if you have a ramp, right? So I can put a ball in here and have it roll down the ramp. If I do that, then it's still one-dimensional motion. I don't have to describe it that way. I could just find my x-axis like that, my y-axis like that, and then have this thing, components along the x and y-axis. That's perfectly valid, but it's just way more complicated than you need. So when you have a problem, the first thing you want to do is figure out what's the smartest choice of my axis to make the problem simple, to make it easy to solve, right? So in this case, I would choose my x-axis to point along this direction, either that way or that way. And I'd stick to my convention. Once you choose it, don't change it. Once I draw this for some problem, I'm not going to switch it halfway and have the sign toggling, because then I'll never make sense of what I'm doing. So is this constant acceleration, this ball rolling down this hill? You won't know even if you did the reading, because we haven't gotten to the part about forces yet. And so far, I'm just asserting what's constant acceleration, so I'll assert it now. This is an example of constant acceleration. So that means you can use those equations to describe the motion of this ball as it rolls down. And just like in a case where initial conditions matter about whether your velocity changes, same thing's true here, right? I can have it go up the hill for a while, comes to 0 velocity, now its velocity speeds up. Well, speeds up. Its speed increases, and its velocity, if this is the positive direction, well, it has positive acceleration then, right? If my x direction points that way, it'd be negative acceleration. And it's not going to be 9.8 meters per second, or 10 meters per second squared, right? It'd be bigger or smaller than that? Smaller. The acceleration of this ball is less than 10 meters per second squared. And you can tell, right? Because when I roll it, it takes a little while for it to get up there, it takes a little while to come back. Whereas if I take the chalk of the ball and I start at the same initial velocity, it comes back a lot faster than it did there. Because this is greater acceleration, greater magnitude. It might be negative, if this convention is negative, but the magnitude of the acceleration is bigger. Yeah. Right, so this is an example of constant acceleration, and we'll see why in a week or two. Right? We'll talk about the causes for these things. Yeah, right? So here's another question. Suppose I got this funny contraption, and I'm going to drop a ball. Who's seen this thing before? You don't know yet. Okay, so I can use this to shoot a ball out one way and drop a ball on the other side. All right, it's pretty fancy contraption. So just what it does. I'm gonna pull the ripcord here, and then this thing will drop the ball, and the ball will fall into gravity, and it'll be shocked by that, and it'll hit the table, right? So if I want to know how long is it going to take for it to hit the table, I can go and do a calculation, and I will. I'll go calculate that. And then we're going to talk about comparing that with motion. This is my little teaser to introduce us to two-dimensional motion. So this guy's going to shoot the ball to the other side. But first, we're going to the dropping ball. So it's the same situation we've already talked about, but now we're going to do this, a ball falling into gravity. But now let's calculate some things. So suppose you're asked, how much time does it take for the ball to hit the table? All right. So how do we do that? Well, we've got the situation right here. Let's go ahead and label some stuff. Oh, we're told in the problem, this ball starts at a height h above the table, right? And we're told that, what else are we told? We're told? Well, we know it's under gravity, so we know what the acceleration is, right? So we know that, we know the physical description of the situation, but now we've got to put some axes on it so we can write our equations down. Let's go ahead and use this convention I drew right here, just for the sake of argument. I'll define this to be my x-axis. I draw it right on my diagram so I don't get confused. Let's go ahead and choose a 0 point, an origin on here. I have two obvious choices. I can make this 0 or this 0. Doesn't matter. I think the probably simplest way to do this would be to make this 0 and have the x-axis point down, but it doesn't matter. It's all the same. So I'm going to call this tick mark here h, and I'm going to call this 0. So those are my two heights. And height is labeled by my x-axis, right? And so now I can ask the question, all right, how much time does it take? Oh yeah, what else do I know? I also know the acceleration, right? So the acceleration of this guy is going to be positive or negative, given my convention. Negative. Negative 10 meters per second squared. I'm just going to refer to this as negative g. So the way I'm typically going to, the notation I'm going to use, both when I solve problems at home, if I'm doing a homework problem or if I'm doing a test problem, or if I'm in class, I'll try to stick to this convention. I define g to be positive 10 meters per second squared. Oh, look at that, I have seconds. Squared. Wrong units on that. So this is a positive constant. Acceleration can be positive or negative. Depends on how I define my x-axis. So this is the convention I'm going to use. I'm just going to use g then as a positive constant I can throw in my equations. Because I want to keep everything symbolic as long as I can before I put my numbers in. That way I can actually just eyeball it and see whether the thing's positive or not. Because I know g is positive. I'm not always sure if a is positive. So that's just an easy way for me to keep that straight. So then what I do is say, all right, well, I'd like to know the time. What equation can I use? Well, the canonical equation, let's see. Well, the bottom equation is no good. There's no time in it. So it's not going to tell me what the time is. It might be an intermediate step. It's not going to solve my problem. The next one's got time in it. It has initial and final velocity in it, though. Right? See the one? I should get a pointer. Look at this equation right here. Right? So this equation right here, I'm looking for time. That's good. I know x naught and x. These are different by h, right? This thing is h. Excuse me. This is h. This is 0, right? But this I know. This I do not know. So this has two unknowns in it. Both t and b are unknowns. One equation and two unknowns is not a solution to make, right? So how about this guy? This one gives me initial. Once again, I have to know the initial and final velocity. I only know the initial velocity right now. What is the initial velocity? 0. And the way the problem will state that is the ball starts from rest. It's dropped from rest. Well, from rest. Okay, 0 velocity. So the first equation really is the one I want, right? Because it has the most terms in it, but it's got time in it, which is what I'm looking for. It's got a, which I know. It's got b naught, which I know. X naught, I know. X I know. Great. So now I can use that. The way I typically do this then is I write everything out, just as it is in the original equation, just so I'm clear on where I got this from. So when I go back and read my notes later, the grader does. They know what the heck I was doing. And then I substitute in the stuff that I know, right? To see if I can. And this is the thing I want. It also appears here, but it's not going to be too bad because what is v naught? It's 0. So this term goes away. What is x naught? It's h. That's right. What is x? That's our final position. Well, that's 0, right? As I defined it. You could have done it a different way, right? You might have chosen this to be 0 and that to be h, and make that your positive x direction. You get the same equation when all the dust settles, right? For example, I told you that the conventions will affect whether your velocity or acceleration are positive in different times in the problem, because velocity changes. Acceleration doesn't always be positive or negative, but it can be one or the other. But your conventions will not change how much time it takes. Your answer better be a positive number with units of seconds, right? It's not going to matter what your conventions are for your axes in terms of how much time it takes for the ball to drop. Okay, so we've got h. This is 0 plus 1/2, and we already decided we're going to refer to a as negative g. So that's negative g. That way I can just eyeball it and see whether it's positive or negative this term, right? And then I got t squared. Great. So now I just isolate for t. Well, I'll do this in 2 steps because you've already seen me make mistakes today, so let's see if I can avoid them. T squared equals, let's see, I added this minus h, and then I'm going to divide by, I'm doing it in 2 steps again. Minus g over 2. Does that look right to everybody? I think that's right. I subtract h from both sides. I multiply both. Oh, I missed a 2. No, it's right there. I'm blind to things on the board. It's really, you should try it. Do your homework on the board. So we got 2 times h, and we got, yeah, I think that's right. So the minus signs now cancel out, and I can just read off that it looks reasonable, right? I'm getting a positive number for t squared. If I got t squared equals a negative number, now we're going in the realm of imaginary numbers and complex, all that stuff. We don't do any imaginary numbers in this class. I know many people will be disappointed. But even in AB, we avoid it, despite the fact that we try to talk about quantum mechanics and stuff, and E&M and everything where it is. It's a useful thing for advanced topics, but we try to avoid it just to make the math simple enough we can focus on the concepts. So imaginary, just so clear what I mean by that, for those who does not know what an imaginary number is? Oh, everybody knows. All right, fine. Don't need to worry about this class. Fine thing. So good. Positive number. We take square root of both sides. What do we get? We get our final expression, 2h over g. Anytime I get a solution, the first thing I do is check to make sure the units are right. And you guys have already caught me making mistakes. If I had propagated those errors through, now I would catch those mistakes because the units would be wrong, right? So let's check, make sure the units are right. What's the units of h? Yeah, h is about a meter. It's like 1 meter, right? It's a meter. G is meters per second squared. Meters divided by meters per second squared is all equal to second squared. Take the square of second squared, you get seconds. Good. The units are units of time. Next thing I do is I look at limits. We did this last time, right? So, but we do it every time. That's the thing. I won't be as pedantic about it through the semester, but I will use it to find errors. It's really helpful. So limits, what do I mean? If h were really big, then it should take longer for the ball to reach the desk for fixed acceleration of gravity. And sure enough, h is on top. You might be bothered by the fact there's a square root here. Say, well, wait a minute, it's a nonlinear function. Does it still work that way? And it does. Square root is monotonic for a positive argument, right? If the bigger this thing gets, the bigger this gets. Even though it's not linear, it's slower than linear, right? It's still the case that a bigger h results in a bigger t, and that, as it must. So that's good. What about g? Say, wait a minute, I can change h by making a taller pole. I can't change g unless I go to Jupiter or going well above the Earth's surface or bore a hole deep in the Earth. But that's okay. As far as the equations are concerned, you can still imagine what would happen if you made g stronger. You turn up the strength of gravity so that acceleration of objects was greater than 10 meters per second squared downward. If that were true, it would take less time for the ball to reach the table if gravity was stronger, right? Sure enough, bigger thing in the denominator, even inside the square root, means this thing would get smaller if this got bigger. See that? So that's how I know when I look at this that I got things right. I trust that even more than I trust that I didn't see any errors in my algebra, because I think through the